We are going to see now the transfer function concept on a mechanical system. This is a system that we have used for other purposes here, but now I am going to use it to understand the basic concept of the transfer function. So on the right hand side, I sort of have outlined the steps that I'm going to follow. One, I am going to find the relationship between an input and an output. So we need to define what the inputs are in here and what the outputs are here. That's a decision that is, individual, subjective decision, which is going to be my output and in relationship to which input I am going to get this so-called transfer function. In order to do this, we have to do step number 2, which is to derive the differential equations. So let's just go one by one. We know what we want to do, and now we are here, derive the differential equations of the system. So why don't we go over here and we say, okay, look, the motion to the right, you have a force in here. We can write a free body diagram to get the forces going. This is the force F over here, and on the side you have the force that is K times X, and this other force that is B times X dot. Yeah? So the equations are obtained where you say summation of the forces external equals to mass times acceleration. So this is the mass M. So why don't we go over here and we say, okay, we say F minus K times X minus B times X dot equals to 0, digamos, or you can say F is equal to this. No, this is not 0. Sorry, M times X double dot is what I mean. For a moment I had a little bit of a distraction in there, but the summation of the forces equals to mass times acceleration. That's what this is saying. Okay, we can write this equation like mx double dot plus bx dot plus k times x is equal to f, you see. So this is my second order differential equation. Okay, so now what we're going to do is we need to define the outputs. So I am going to say here what is my input in here. This is F, yeah. What are my outputs? For example, in here we could say the velocity of the mass, maybe, velocity of m, and the force acting on the spring. Yeah, these are the outputs. So what we are seeing, we say we want, you could say, a relationship we want a relationship between, in this case, the velocity of the mass in relationship to the force input, and we also want the force on the spring in relationship to the input. These are the things we need to find out. Okay? So we have derived the system equation right here, and then we need to apply the Laplace transform. This thing in here, I'm going to call it a transfer function 1, and this is going to be called transfer function 2. So the relationship between the velocity of the mass to F is transfer function 1, relationship of the force acting on the spring is transfer function number 2. So how do we actually get started on this? We need to understand the Laplace operator that says clearly that d of any function, d dt of any function is equal to s dot. Now d dt is s, excuse me. That's the whole thing. This was the basic principle for the Laplace operator. This is called the Laplace operator. The Laplace operator. So if I do d of dx dt, this is going to be s times x, times x of s. If you do d square dt square, this is called s square times so in here we can write using this transformation. We can write over here, so we can say that m times x double dot, which is this one right here, times s squared times x of s. So let's just see ms squared times x of s like this, plus b times x dot, which is in this case is s, and then bs times x of s like this, right? And what else do we have? As this plus k times x of s equals to f of s. So just get the x of s out, and you have ms squared and then you have plus k all with x of s out. Yeah. So it's clear to me that the state variable x of s is equal to 1 over see it's 1 over ms squared plus bs plus k multiplied by x of s. No, x of s is 1 over this is times f okay. So this thing in here is called a transfer function. It's called a transfer function. Okay, so now that we have said, remember what do we want? The velocity of the mass. Velocity of the mass is equal to x dot. Yeah? In this particular case, velocity of the mass equals to x dot. If we transform in the Laplace domain, the velocity of the mass is going to be s squared times x of s. So if I know this expression and I know this, I should be able to find my transfer function. So remember, this would be velocity of the mass divided by okay, so this is, but we want velocity of mass divided by the input like this, right? Don't we? So this is s squared times x of s, which is 1 over ms squared plus bs plus k, times f of s. So it follows now that the velocity of m in relationship to the input is s squared plus bs plus k, and this is our transfer function. Okay, so that's the transfer function. But remember, that was not the only one that we wanted. The force on the spring, this force here is K times X. That's the force on the spring. So force on the spring is K times X. So if you have F of the string of S is equal to K times X of S. And this X of S we do have, see? This X of S 1 over M S squared plus BS plus K. Then times F of S. So in this case you have F of the spring of S divided by F of S. So let me erase this a little bit in here. So we have this rho in here over ms squared plus bs plus k, and that too is the transfer function that we were looking for. And this, of course, this too is the transfer function. You can do this with any system to obtain these transfer functions. There's relationships between the output and the input. So this is our transfer function in the doing it in manual way. Now what we can do is do the same thing but use the ChemG software. And now we will instead of deriving it by hand here, we're gonna look that the computer will do it for me. In order to do that, I am gonna go ahead and copy this perhaps, and I'll start over here and build the bond graph model first. How do we do that? We put the one junction for the velocity x dot. We attach the source of effort on the side with value f. We have in here the C element with value 1 over k, and then over here we have the R element with value B dot. And then of course the inertia, with value of the mass. So this bond graph model, we need to enter it into ChemG. Let's just fix it up a little bit in here to make it look pretty. I'm not going to change it, but I mean, this is the source of effort, which is like this, and then of course here is the R element. I'll just put the 1 and 2 and 3 and 4, and I'm going to we could complete the causality assignment if we wanted to, but ChemG will take it as is, so just to make that point. So in here we're gonna go and have the program run over here, QMG, and then you go over here. We're gonna go and produce that same bond graph that you see here. Yeah, that one. And this is gonna go here. Say okay. Where is the mouse? We still have the program alive. It's just that I am not able to see the mouse right now. We lost the control of the computer. I'm not able to see the mouse anymore. That's too bad. Anybody has any idea why? Well, we need to also stop the I've never had this happen to me. It's almost as if, can you imagine how much of a influence the mouse is? Okay, good. I think we're back. I have no idea. We have to get this. I think what we're gonna do is let's stop the video before we lose that thing. Stop this, right?